Hello. So here I'm going to consider the simplest possible example of the binary distribution. That's the coin flip example, right? So in a coin toss, I'm going to define a random variable x this way. So I will encode heads as 1 and tails as 0. And we are going to call heads as success and tails as failure. But as I said, it doesn't matter if you change like a 1 or 0 and success and failure. It's just matter of encoding, so labeling. So relabeling does not change the analysis. Of course, it may change the numerical results, but the basic structure of the randomness does not depend on which you call 1 or 0. And suppose that you toss a coin 5 times and you got these observations like heads, tails, tails, right? So instead of heads and tails, I'm going to write them 1, 0, 1, 0, 0, right? So from this sample, finite sample, first we would like to calculate the probability of heads from the observations. So it is simple, but try. And when you're done, turn the page, otherwise pause the video. The probability of heads is out of 5 times, simply out of 5 times, you got heads twice. So the probability should be 2 over 5, which is 40%, right? From that sample, according to the data, the probability of success is 40%. Now, from the same data, what is the mean of the observations? They are numbers, so you can calculate the mean. And what is that? Try this, pause the video, and do the algebra. And if you're done, okay, the answer is this. It's simple. Just add all the 5 numbers and divide by the sample size 5, which is pretty simple. And you know, this is the raw data, so you have to use this way. And the result is, again, 0.4. So the mean is 0.4, which happens to be the same as the probability of heads. But actually, it's not a coincidence. This is one of the key properties of the binary distribution. So the idea is, so in a binary distribution, always the observations are either 0 or 1. 0 or 1, then the sum of the number of successes is number of ones. 1 is success, so number of success is 1. And if you sum all the numbers, also that equals to the number of ones, because zeros do not affect the sum. So the sum of the numbers, the sum of zeros and ones, depends only on how many ones there are, right? So like counting how many ones is equivalent to sum those numbers, right? So if you find it, so try this. Like write down by yourself, write down like randomly 1, 0, 1, 0, whatever, zeros and ones. And then try sum all those numbers and then count how many ones you have. They must be the same, no matter what combinations you write, right? So number of successes, which is number of ones, is always the sum of observations. This is the underlying property of the binary distribution. So as a result, when you calculate the probability, you count the number of successes, divide by sample size. And when you calculate the mean, you sum the observations and then divide by the same sample size. But as I said, as we just discussed, the numerators are the same. So all those two guys are the same. So the probability of success always equals the mean. That's one of the important properties of a binary distribution. So then we can think it we can utilize that property when you interpret the mean. So think about this. I said the mean is 0.4. What is that? Actually, it has no meaning because 1 and 0 are just labels. They have no numerical meaning, right? So I just put 1 into success and 0 into failure, but you could use like 1 or 2, or like 100 and minus 100. It doesn't matter. It's just labels. So they are not numbers. Actually they are numbers because we need numbers. But it doesn't mean that 1 is greater than 0, right? So so they are numbers just because we needed numbers. So that causes a problem in interpretation. When you interpret the mean, 0.4 is not a possible outcome. So in between heads and tails, there is nothing. There is nothing in between heads and tails. So then, how can we interpret that? You should interpret the mean as the probability of success. We just learned the mean always the same as the probability of success. So I strongly encourage you to interpret the mean as the probability. So 0.4 means the probability of heads is 0.4. That's the mean. But so interchanging between the mean and the probability is possible in the binary distribution model. And then what's nice about this is the probability and the mean are the same. That means they share their nice properties. For example, there are some statistical methods that can be applied to the mean, but not for the probability. But still, we may borrow the methods when you interpret the probability as the mean. So like the probability of success has all the properties as a mean. So we may do more analysis either by interpreting it as a mean or as a probability. So both methods apply to the same parameter. That's a nice property of the binary distribution. Okay, so then let's think about our homework. Homework is another example of binary choice. So in your homework assignment, there are 5 choices. Multiple choice questions have 5 choices, and say x is the random variable of your your grade. X is your grade from that question. So you get a question, but you have no idea what it means or how to solve that question. So you randomly choose one answer. Then you are going to get 1 point if your randomly chosen answer is correct, and 0 if not, if wrong. And in this case, 1 and 0 are kind of like has meanings, and so it is natural to call success when you choose the correct answer and failure when you choose the wrong answer. And we know because there are 5 choices and there is only one correct answer, the probability of choosing a correct answer is 1 out of 5, which is 20%. So this setup, when you randomly choose one choice out of from a multiple choice question with 5 choices, then the result is a binary distribution. Exactly, it's a perfect example of a binary distribution with probability 20%. And in this case, you know the probability distribution, and now I'm asking you to find the mean. What is the expected point you get when you randomly choose an answer? Oh, excuse me. So, right, if you have done, let's turn the page. The answer is 0.2 because the mean is the same as the probability of success. Always. Without calculating, without using the numbers, you can just choose 0.2. But just in case, if you cannot believe, if you don't understand what's going on, then you could try this way. Remember, the mean is the sum of probability weighted outcomes. So we multiply the outcome to the probability, 0.2. Outcome to the probability, 0. Sum, 0.2. So as it should be, 0.2 is the mean. Okay, now the next step is to find the variance. What is the variance of your grade if you randomly choose an answer? Pause the video, it may take more time. Pause the video and do the work, and resume when you are done. So, to calculate the variance, we know the mean, so you need to make a squared deviation column. So I just originally in chapter 4 I made like separate columns for deviations and squared deviations, but I did them in one step. So deviation is 1 minus mean and 0 minus mean, the outcomes minus the mean, and square them, square deviations. So we get 0.64 and 0.04. And remember, this squared deviation is a transformed random variable with the same probability. And we are calculating the variance is the mean of these squared deviations. So multiply probability weighted outcome is 0.2 times 0.64, which is weighted square deviation is 0.128. And probability times outcome 0.032. Sum them, then you get 0.16, which is the variance, right? So the variance of this distribution is 0.16. And then you even though I do not use any properties of the binary distribution, but you could imagine that the parameter must have some relationship, must have some impact on the variance. We can easily deduce that by generalizing, making it abstract algebra. So I'm going to, generically, I will put the success probability as P. That is the parameter. Then the failure probability is automatically 1 minus P. And with these unknowns, we can still calculate the mean. So as we did with these numbers, we are going to do the same thing. Multiply the outcome to its probability. 1 times P is P. 0 times 1 minus P is 0. Sum them, that is P. So this is how we prove the equivalence of the mean and the success probability. Right? So it is just confirmation of what we do. But variance is a little bit more complicated. So, but we are doing the same thing using the abstract unknown P. Deviation is, the mean was P, and the deviation is 1 minus P and 0 minus P. And you square them, and this guy is a transformed random variable. Multiply each of the possible outcomes to their respective probability. So P times outcome this way, and 1 minus P probability times outcome this way. So minus P is this one, deviation. So if you add these two guys, expand the square and calculate to simple math, then in the end you get minus P squared plus P. Like the cubic terms canceled out. And then you can simplify it to p times 1 minus p. This is the relationship between the parameter and the variance. And what you can see from here is variance depends only on the parameter. So that means if you know the parameter p, then you can easily calculate the variance. Calculating the variance is not a problem at all once you have the parameter value. So then this is the formula. So variance is simply the product of success probability and failure probability, right? Success probability, failure probability. And in our example of homework, the homework randomization example, the parameter was 0.2, and then the variance could be calculated this way: success probability times failure probability, which is 0.16, exactly the same variance as we calculated. So again, the point here is we need only one parameter, p. Like if you know the parameter p, then we have the full distribution table. Probability of success, probability of failure, and then we could calculate the mean and the variance. So this is an example of scientific model simplification by assumptions. So one parameter can do everything in binary distribution. And this is one so the intuition behind, by the way, a relationship between p and the variance, parameter p and the variance. What's interesting here is it's a p times 1 minus p. So if you think about the probability of success, if the probability of success is 0, then variance is 0. But if the probability of success increases to 10%, 20%, and then 50%, the variance also increases in this order. And then after 50%, it decreases again, but it's symmetric. So when the probability of success is 100% again, then the variance is 0. So I would like to explain the intuition behind it. So remember, the variance is a measure of variability. Simply, it's about how much the outcome varies, or I would interpret it as a kind of uncertainty or predictability, right? The larger the variance is, the less predictable or the more uncertain the outcomes are. So in this case, when the probability of success is 0 or 1, these are extreme cases where the outcome is either always failure or always success. Always failure and always success. That means the outcome is constant. There is no uncertainty. It's perfectly predictable. You know what is coming, right? So when you toss a coin, it is always heads. Then the variance is 0 because there is no uncertainty, no variability. On the other hand, in the middle, like 50%, this is where the uncertainty is maximized. So when the heads and tails are 50-50, your whatever you predict, you are wrong with 50%. So there is no better prediction at all. It's perfect, uncertain, chaotic situation. So that's why the variance is maximized. You cannot predict at all. But as an example, let's think about 10%. When the probability of success is 10%, then I would predict failure. Failure happens 90%. So you are correct 90%. So there is uncertainty of 10%, but that's smaller when you compare to 50% case. So as you have 0 or 1, there is no uncertainty. But uncertainty is maximized in the middle, 50%, because you cannot either predict heads or tails. Both are equally wrong, equally correct, so prediction is meaningless. Okay, so this is a basic property of a binary distribution. So binary distribution is simple, but it's a nice example to understand what we are going to do and why we are doing this. Okay, we are in the next video. I will extend the binary distribution to a binomial distribution, which is much more complicated. So, but we are using the same properties. So make sure you understand those properties. Okay, see you in the next video.